It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on root biohydromechanical reinforcement of unsaturated soils, experiments and modeling was delivered by Professor Anthony Leung at this workshop. Dr. Anthony Leung is an Associate Professor in the Civil and Environmental Engineering and the Associate Director of the Geotechnical Centrifuge Facility at the Hong Kong University of Science and Technology. His research expertise is unsaturated soil-plant interaction with emphasis on geotechnical engineering applications such as slope stabilization. Dr. Leung has published more than 70 SCI journal articles in the subject of soil-vegetation interaction and co-authored a textbook Plant-Soil Slope Interaction published by Taylor and Francis. Dr. Leung is the awardee of the 2019 Excellent Youth Scholar, EYS, of the NSFC, 2019 Bright Spark Lecture Award of the ISSMGE and 2018 International Award for Innovation in Unsaturated Soil Mechanics from TC106. He is currently the Editor-in-Chief of the ISSMGE Bulletin, the Secretary of TC106 and TC107 and is now serving the editorial boards of international journals, including Canadian Geotechnical Journal and Landslides Proceedings of Institution of Civil Engineers, Environmental Geotechnics and Proceedings of the Institution of Civil Engineers, International Journal of Physical Modeling and Geotechnics.
So thank you once again for the organizer having me today to share some of my recent work that I've been working on this rooted soil or vegetated soil. It's a very long title of my presentation here, but I'll try to make it concise in the next 45 minutes of my presentation, focusing mainly on experiments and modeling. Okay, so yeah, as the organizer introduced, I'm working in the HKUST, Hong Kong University of Science and Technology, and this is the outline of my talk today, focusing first of all to let you know why vegetation on soil hydrology or particularly slope stability problems. So then I will split my presentation in three parts, looking at the two major functions from plants in engineering perspective: mechanical reinforcement and so-called hydrological reinforcement in the first two parts. So in the third part, I will try to integrate some state-of-the-art understandings in these two areas, mechanical and hydrological reinforcement, to numerically model how plants could perhaps stabilize soil slopes, and then come up with some conclusions. So what is the role of vegetation on slope stability? Well, it's an environmentally and ecologically friendly approach, which gives you a very aesthetically pleasing appearance on the slope. And you could enhance biodiversity, increase the ecological restoration, and importantly, to offset some carbon. But from engineering perspective, it's actually, they can have some important functions to slope or soil stabilization. So broadly speaking, as I earlier introduced, we can say mechanical reinforcement. So basically, it's using plant roots, to increase the shear strength of the soil. And that has been studied quite a while in the literature, the mechanical reinforcement. But more recently, in the last 10 years, we have been working on hydrological effect on transpiration, because that is one of the important plant physiology to respond to the atmosphere vapor demand, so that the water uptake from the soil could have affected the moisture content. So from unsaturated soil perspective, perhaps that could, the suction, the matrix suction induced in the unsaturated soil could have also contributed to the slope stabilization. So this is always the research question that we have been asking in the last 10 years on the hydrological reinforcement. So moving to the part one, although the mechanical root reinforcement has been studied quite a while in the last 40, 50 years, but we try to revisit some of them very carefully, and we do identify some interesting stuff that has not been fully attended in the previous work. And these are just the relevant publications that we have been working on in recent years. If you're interested in further details, just feel free to take a look. I think the last paper here, the ASC one, is just in press and is available in the general website. Okay, so these are the publications that I'll be using in my presentation today. So one of the major research questions that we have been asking in mechanical reinforcement, which is a quite old topic, is, okay, slip surface is not always parallel to slope surface. So as you can see, this is a potential slip surface on a bioengineered slope. In this case, it's a vetiver grass, okay, which is quite commonly seen in India, I believe. And if you look at the stress state of this soil along this slip surface, okay, and there is a rotation of major and minor principal stresses, okay. And if you look at the stress state of each individual elements, and these stress states are rotating. So normally in the literature, we have been using a direct shear box as a major tool to quantify the root reinforcement effects for slope stabilization. However, if you look at other positions of that slip, close to the crest, you may have a triaxial compression-like stress condition. But if you look at the toe, there will be some kind of a triaxial extension stress state to the soil sample. So, so along this rotation of the stress state, the reinforcement effect also depends on the root orientation, because whether the reinforcement is giving to the soil effectively depends the relative orientation between the root growth and also the major principal stress. So in other words, if you put the same plant in different positions of that slip, you will have a different reinforcement effect. So in short, we couldn't simply assume whatever we obtain from direct shear box test could be equally applied in other different places of the slip plane. Okay, we have to be careful on this, and that is the research question we have been asking in this part of the research. So that leads to the objectives here. We aim to study how the effect of stress path, which I mean is the compression and extension on the shearing behavior of saturated reinforced soils. Now, rooted soil is a very complicated material to deal with. So we wanted to start from something very simple, which means saturated, before we move to the unsaturated, because the stress path could, which I will show you later on, give us some quite interesting results, but challenging to interpret. So we will stay with saturated in this part of my research. And then another objective is to compare the shear strain parameters obtained from different stress paths to investigate whether that different orientation of the major principal stresses with respect to the orientation of the root direction could play a role on the root reinforcement. So moving to the materials, and we have been using is the vetiver grass. Again, it's quite a very impressive ecological engineer, we call it, for slope stabilization, just because it has a very deep-rooted characteristic, and it has a pretty strong the root tensile properties for slope stabilization. It's native to India, but also commonly found in many Southeast Asian countries, including Hong Kong. We do find some in some of our slopes. So as I said, it's a very extensive root system, deep-rooted, which is very favorable for slope stabilization, especially for shallow slopes. Vegetation as a bioengineering method has been challenged by the very shallow-rooted, but for this particular species, it can go even deep to 7 meters or even 10 meters, depending on the soil type and the environment. So it's a very good ecological engineer for this purpose. So for soil, we use relatively simple materials, touracin, a standard material, so that we already fully understand its mechanical properties before introducing the root. So it has a relatively uniform graded, uniform graded material with these coefficients of uniformity and curvature. So you may wonder, how do we grow the vetiver in such kind of standard materials? So instead of growing the plant into the soil, we made artificial sample, okay? Again, this is just because we can have full control on what we have inside the soil, okay? So what we did is we collected some tillers of vetiver from the nursery, and then we collected some individual roots that have that range of diameter, so that we know exactly what type of roots we are working on in the specimen. And by putting all these roots together in the triaxial mode, we have a root volume ratio of 0.45%, which is defined as a root volume divided by the whole soil volume within the triaxial sample. So this is quite commonly found within the range of the root volume we will find in the literature. So that is a triaxial specimen size, it's pretty standard. And the density we're working on is 1,500 kilogram per meter cube. Again, purposely making it something more realistic to the field condition, because the plant doesn't like a very dense soil. So this is something quite realistic for the plant to grow, to mimic the conditions, although we didn't grow it in our specimen. So as I said, it's not ideal, it's not a very, representative samples in the field, but we do acknowledge this, the major advantages to have the full control of the root properties. We exactly know how the root distributed, and we know what kind of root morphology by the root scanning, and then we know the diameter, length, volume, all information, even the orientation, which is very important to interpret the stress path effect in our particular objective. And another advantage is we can do repeatable tests for comparisons. So I hope you would agree with me, if you even grow your samples under identical environmental condition, you wouldn't be very easy to obtain repeatable samples for direct comparison. So that is one of the major purposes of using artificial sample in our case. So once we have attached this root onto the pedestal of the triaxial cell, we apply the sand deposition to create our samples of that dimension and that density. So we use a pretty standard triaxial equipment, which we call it a CKC equipment in our laboratory, which is computerized to control the stress path to our under our control. So we can apply exactly triaxial compression and triaxial extension to the samples by carefully controlling the B value, which is 0 for compression case and 1 for the extension case. Okay. And yeah, so this is pretty standard, and I wouldn't go into details. And that is the test plan. So basically, we have two types of samples, bare and a rooted sample. So we have a large series of tests, including compression and extension tests, and looking at this one root volume ratio and also different confining pressures, so that we can obtain the cohesion and friction angle later on. Okay, so these are just the volume ratio that I've been created after the sample preparation. Okay, so the test procedure is again very standard for saturated shearing test, which is a back pressure saturation, and then we consolidate the material to the effective confining pressure that we wanted, and then apply a drain shearing to under a strain control condition by applying this compression extension. So that is a standard procedures in our tests. Oops, I apologize. I should have skipped this. Okay, so now here's the results for the from the test program. So what you see here is the stress strain curve, the directoric stress and strain curve for bare soils at different confining pressures. So as you could imagine, the higher confining pressure, the higher shear stress or the shear strength provided by the soil, and you can see a strain hardening response along the compression path. If I superimpose the responses from rooted soil along the compression path, you will see the dotted lines over there, and you see that the root effect is more prominent at relatively large strain rather than in small strain, so that the root will gain sufficient, the tensile strength to develop the tensile resistance to the soil. And that's why we see a more significant increase in shear stress in a larger strain rather than in the smaller one. So now if you look at the strain, the stress behavior in the extension path. Oh, again, these are the solid lines representing the extension behavior for the bare soil. And then if you compare the responses from the rooted soil, you see the dotted lines again. The root effect is much more significant. And if you compare to the responses to the bare soil, the hardening behavior disappears. You see some sort of a quasi-steady state here after reaching a peak. Okay, so that is different. Is a different behavior from what you observe from the bare soil. So this is somehow sort of the raw data of the response we obtain from a triaxial test. But the important message here is the behavior of rooted soil is anisotropic. As one can, imagine easily, because the root orientation cannot would have a very different orientation as your major principal stresses, even in direct shear box. Just this is one of the very early set of data that demonstrate the anisotropy behavior of rooted soil. So since we have been looking at different confining pressure, we are able to plot the data in the mole coulomb envelope framework. So if you look at the table on top here, they are the compression data for the cohesion and also friction angle for bare and rooted soil. Okay, so the summary here is for bare soil, you will see the friction angle is around 35 degrees. Okay, so then for extension path, I should have mentioned that here. So the rooted soil doesn't have much increase in friction angle compared with the bare soil. You see only 2 degrees, perhaps not very much significant. Okay, and we didn't observe much increase in cohesion, both 0 in the in this particular case, just because the Toyota sand is cohesionless, so we do not expect any true cohesion or true bonding between the particles. So if you look at the extension path, the friction angle for bare soil is 41 degrees. Okay, so and then if you move on to the results from the rooted soil, you see a much more significant increase in your friction angle by almost 10 degrees if you compare this. And that happens for relatively low confining pressure. But if you look at the high confining pressure here, the friction angle is almost the same as the bare soil. Okay, so in other words, the failure envelope for the rooted soil in the extension path is nonlinear rather than linear. Okay, and root works much harder in the soil to reinforce the soil at low confining pressure. Okay, that's the observation. And one thing interesting to note is that you do see the cohesion from the extension results, like what you see in the typical direct shear box. Because in the literature, the direct shear box test always give you a root cohesion and nothing changed in the friction angle. Okay, but here we see quite a different result because the friction angle has been increased quite significantly in addition to the increase in cohesion. And that cohesion basically is because of the bonding. Not by the part, not by the root, by the soil, but by the bonding, apparent bonding by the roots. So they wrap, they tangle the particles together to form a composite, and that's where the cohesion comes from. Okay, it's quite interesting to observe this. And what does that mean to slope stability? Okay, so before that, the key observations is root effects on friction angle vary with stress test. So depending whether it's compression, extension, or even direct shear path. So the friction angle could have changes by rooted soil. Okay, and the reinforcement effect is anisotropic and path dependent. So for deep-rooted soil and for deep-rooted species, the reinforcement along the compression curve was much less than the extension curve, just because imagine the major principal stress for compression is in the vertical direction, which aligns the direction of the major root growth orientation. So in this case, it's not a root growth, but a root orientation in our artificial sample. So if they're parallel, they couldn't the roots really couldn't mobilize much of their tensile strength to resist the shearing. However, for the extension path, when the major principal stress is in the horizontal direction and perpendicular to the root orientation, then we maximize the root reinforcement effect. And that's one of the underlying reasons why the friction angle has been increasing quite significantly along the extension path when the confining pressure is low. Okay, so so that's the major conclusion. Roots mobilize their tensile strength the most along extension path. Okay, so that also sort of not conclude, but it's quite different from what we observe from direct shear box tests in the literature, which normally says that the friction angle didn't change and only increased the cohesion. That is just because they are looking at one particular stress path rather than in a general along different parts of the slip surface. So what does that mean to the slope design? Now, if assuming the friction angle to be unchanged may not be always true because it depends where you're talking about along the slip surface. Maybe true along the direct shear box stress path, But if we do consider deep-rooted species like the vetiver, it may be the best, to put your, as a good practice of vegetation management, to put this kind of species near the slope toe, because by that position, the soil is experiencing extension path, and the root orientation by the vetiver could maximize its reinforcement effect. So in other words, although we didn't do an experiment, but we can hypothesize at this stage, if you want to reinforce the slope in the crest side of the slope, then perhaps you want to look for more laterally rooted species rather than deep-rooted as optimized vegetation management. And in fact, for slope design from landscape perspective, you would want to have a more diversified species, from landscape perspective rather than mono species on the slope. So it would make sense to have another species that perhaps laterally rooted so that it can reinforce your soil near the crest more effectively along the compression path. Okay, so that is the implication to this comprehensive triaxial test results. Okay, so that's conclude my first part of my talk on the mechanical reinforcement. So now I'll be moving on the second part of my talk, which focuses on the hydrological reinforcement. Again, these are the publications that we have been published in the last 5 years and will be using in my presentation. So what is hydrological reinforcement? As I hinted earlier in the introduction, the plant will transpire because of the physiological needed for its growth. So the root water uptake is a process of soil drying. So again, from the unsaturated soil perspective, the soil drying would induce suction, which means negative pore pressure, which have some implication to the permeability and also shear strength of the soil. And they are very important for slope stability design. So transpiration has been recognized as the most important or most recognized hydrological effect by plants on the soil. But now we are trying to identify some other potential hydrological effect. And here what we are hypothesizing at the beginning is whether roots could also affect the pore size distribution, which directly affect the water retention curve and permeability function. And they are very important hydrological properties to predict the soil water pore pressure distribution in the slope. So in the previous studies, they have been assuming the root would not affect these two properties. So we are making a hypothesis the root growth along within the pore space could have affected these two parameters. Okay, so this is the major research question we want to address in this part of the research. So before looking at the experimental responses, we thought about it from more theoretical perspective. And this is a phase diagram of a bare soil without any roots. So this is unsaturated soil, so you expect 3 phases: air, water, and solid. But if you have the rooted soil here, and you have a new phase called roots, and that occupies part of the volume of the soil. And if you also consider some possibility of decaying of the roots when during the root growth, then some void will be returned to the soil. Okay, and you have another parameter to describe the volume of the root return to the soil. Okay, so this is a basic theoretical consideration of the phase diagram for rooted soil before and after decay. Okay, so by working on this mass volume relationship of this rooted unsaturated soil, you can come up with this new void ratio function for it. Okay, and there are 3 parameters. The first one is the initial void ratio of the bare soil before growing. And then you have also 2 root parameters, which one of them is describing how much occupants in the root and in the pore space of the roots. Okay, so we are hypothesizing the root effects is physical and ignore the biochemical effects like the exudate or the mucilage released from the root tip. So this is a physical model which considering the root occupation is in the soil pore space. And we do have another parameter called the eta here to describe the root decay, depending on the proportion in the soil. So with these 2 parameters, we can predict or estimate the void ratio of rooted soil. considering the root decay or root growth. Okay, so so this is the definition of the root volume ratio, which I have used in the first part of my talk. And what we are concerning about is the water retention curve. Okay, so we recall this the famous water retention curve for deformable soil from Gallipoli et al. 2003, published in Geotechnics. So what we are doing here is just to put our new vol ratio function into that existing water retention curve equation, so that we can capture the root effect. Okay, so the blue symbols here represent those existing parameters from the water retention curve, and the red one here represent the new the vol ratio associated with the root effect. Okay, so these are just some sensitivity, calculation using this simple equation. This is a water retention curve plotting the degree of saturation and the matrix suction. So the black line here represents the bare soil before any root occupation. So if you increase the root volume ratio without considering any decay, you will see an increase in water retention. So you see a higher water retention for a given suction. Okay, that makes sense, because when the root growth in the pore size, you basically create some apparent densification to the soil. The soil feel denser. They feel denser. That's why you feel a stronger water retention ability in the soil. So if you look at the decay effect by parametrically changing this active value, you will see a decrease in the water retention. Okay, that again makes sense, because when the roots return the pore space to the soil, you create a more apparent loosening effect to the soil, and that's why you have a reduction of the water retention effect on the curve. Okay, so now let's verify the theoretical consideration of our model. So what we did in the HKUST lab here is to produce a lot of this kind of drums, I call it, with a diameter of 60 centimeters, pretty large drum with a lot of plant inside, and considering different plant spacing effects. The plant spacing here is just a laboratory means to introduce decay in the root. Just because when they put together closer, let's say 60 millimeter, they will have more, competition of nutrient, of water and other nutrient as well. So that would accelerate the root decay from the agricultural literature. So that is what we try to, increase the amount of root decay by having a closer plant spacing. And the species we have been using here in this case is a Cephalaria heptaphylla, another very commonly used landscape species in roadside slopes. The soil type we use is the completely decomposed granite, commonly found in Hong Kong, which is well-graded sand with silt, and with this saturated permeability. So the test procedures are pretty straightforward. We grow the plant, we irrigate it during the growth period, and then during the real test scenario, we let the plant to grow to drought, subject to drought for a week. And you see some holes over there, which are the instrumentation for tensiometer and moisture probe to obtain the matrix suction and water contact. So by doing so, you can construct the water retention curve. And before we show the curve, and we're also interested in the root distribution or the root morphology, just because you need the parameters to calibrate our theoretical model, the RV parameters and also the eta in the water retention curve. So here you can see when the plant spacing increases, the root biomass apparently increases just because it has more space to grow. The 60 millimeter is just like, in Hong Kong, we are very crowded. It doesn't have space to grow. And then you have a very localized root biomass and less extensive than the 180 millimeter case. So we do identify some root decay. If you look at this little image over there, by identifying the brittleness of the root. Then by careful counting, then we are able to quantify the eta as well as a root decay proportion. So by looking at this root morphology using the scanner, we can then determine the root volume ratio as well at different plant spacing cases. Okay, now we have all the parameters and we are ready for predicting the water retention curve. So this is the measurements first on the data point. So you see the black line again representing the bare soil. So for the S60, which is the, let's look at the large spacing case first, 180. So the root decay proportion is much less. And the root occupants effect is more significant than the root decay effect. So again, that causes some apparent soil densification, and that's why we have an increased water retention. And the prediction is pretty well in our case. And oppositely, if you look at the closer spacing case, the root decay will play a more significant role, causing soil loosening and then reducing the water retention. Okay, so that's the observation to confirm our hypothesis on the plants really trying to occupy or affecting the pore size distribution and then affecting the water retention curve in this case. So we also found that the so-called hydrological reinforcement is not necessarily or exclusively only coming from the transpiration, but also potentially affecting the soil hydraulic parameters, which perhaps can be also included this so-called hydrological reinforcement. Okay, so that's some of the major findings we have in the second part. So now let's move on to the third part. So what does all this mean to slope stability? So at the end of the day, we are engineers rather than farmer. Like myself now, we are moving to as a farmer, but we are engineer at the end of the day to design our slope. So what does those mean? You know, the mechanical and hydrological effects on slope stabilization. Okay, again, these are the two related publications that I've been using in the subsequent presentation. So in this modeling, we consider a relatively simple model, which is an infinite unsaturated vegetated soil slope. Just for us to more easily considering the root effect to start from. So the water table we consider is somewhere below the slip surface, so that we are dealing with unsaturated material, and we consider this a parallel vegetated layer which contain the roots. And hypothetically, we have this failure surface so that we can work on the factor of safety along that particular slip surface. Okay, so before we do the stability calculation, we need to know the pore water pressure distribution. So we need to model the slope hydrology as well by considering seepage. And since this is a simple model, then we utilize this one-dimensional transient seepage, which basically is the Richard equation together with the Darcy's law to formulate this governing equation of water flow in the soil. So the physical meaning of these terms basically is, you consider one soil element that you have inflow and outflow, and then you have some storage, and that storage of water is because of the water retention ability of the soil. And that is represented by the left-hand side equation here. So the right-hand side, the red term here represent the inflow at the change of flow rate when the water flow through that particular element. And you do see this sink term, so-called, to represent the roots effect. So this is taking into account the plant transpiration effect that has been considered in the many literature. So I will later on introduce you how the root-induced changes in the water retention be considered later. So this is only considering the transpiration effect by sink term. Okay, so in this modeling, we also consider different root architecture on how would that perhaps affect the water retention curve. So these are the idealized distribution of root volume of different root architecture, triangular shape, uniform, parabolic, and inversely triangular. So with this idealized root architecture, we can then have a known root volume ratio, the RV, which is necessary to our model in the second part. So again, utilizing this new vol ratio function and considering no decay by inputting to the famous Calipoli water retention equation, then we can predict how would the water retention curve be affected by the roots. And note that this is the water retention curve at one depth. For uniform distribution is fine because all this water retention curve will be the same along the depth. But if you look at this parabolic shape, for example, and they have a varying RV along depth. So that means they should have a different water retention curve along depth. Okay, so this curve only represents one particular depth within the root zone. And in our modeling, we consider this varying water retention along depth, depending on the root architecture. Okay, so in addition to water retention, hydraulic conductivity function or a permeability function is also a very important parameter in modeling seepage. Okay, so in this case, we rather than using any new theoretical model for permeability function, we use this Van Gunneten model for prediction from the water retention curve. Okay, so what we only need is the saturated permeability, and then with this equation, then we can predict unsaturated permeability function. Okay, so this is the approach we have been using. And again, we are using this simple equation, empirical equation, to capture how the void ratio being affecting your saturated permeability. Because fundamentally, permeability in saturated state is a function, it's a sole function of a void ratio. So if you use this new void ratio function to capture the effect of RV, then we can then estimate how the saturated permeability be affected as well. So that is the result. So you can see a mirror image of this root volume ratio for this saturated permeability. Just because you have higher volume ratio, then you have a higher void ratio, then you have a lower permeability. Okay, so whatever below the root zone will stay the same as the bare soil because you don't have any root to affect your void ratio. So that is the input to our model. Okay, so let's take a look on the soil and the slope hydrology before we move to the stability. And that solid line here, so this plot is showing the suction along that, okay? And the solid line represents the hydrostatic condition before rainfall. So now we impose a rainfall of 70 millimeter per hour to the slope and see how the suction responses, okay? So these lines represent different root architecture, okay? So you do see some effects on root architecture on the distribution of suction. So, the important conclusion here is you found that most of the suction disappear in root zone, as you may be expected, just because the rainfall happens on the ground surface, and then you will have a high hydraulic gradient to destroy the suction. But important is in deeper depth, some suction did preserve compared to the bare soil, which is the dotted line here without the roots. So you do see some additional suction preserved in deeper depth, which is important for slope stability. Okay, we are talking about 2 meter, 1 meter kind of depth of failure. So this suction is quite important for slope stability perspective. Okay, so that is the major conclusion. And from numerical modeling, we are able to extract the water balance components in the calculation. So what I meant, water balance is you can obtain the runoff, the evapotranspiration during the rainfall period, and also the amount of water going into the soil. So the bare soil, as you may expect, most of the water goes to the soil, only need to go to runoff or evaporation, okay? And then you see this root architecture effects has not very significant changes in the amount of infiltration. They're more or less similar. And you see, quite surprisingly, or quite interestingly, I would say, is the evapotranspiration, which represented by the black shaded region here, is very little, even the plant exists during this 24-hour of rainfall. So in other words, during this 1 day of rainfall, the amount of water evapotranspirated to the atmosphere is very little compared to the infiltration, okay? So transpiration effect did happen, but it's not so significant just within 1 day of the heavy rainfall, okay? So then we wonder what happened to the soil then. So why would that affecting the only affecting the hydrology that little. So this suction preserve mainly is because of the root-induced changes in the hydraulic properties, water retention curve, and hydraulic conductivity function, okay, rather than transpiration. So that highlights the importance of considering that part of hydrological reinforcement that are introduced in the second part, in addition to the transpiration effect, okay? So, so now let's go back to this infinite slope, looking at this factor of safety. So by having this simple geometry, we can work out the factor of safety pretty straightforward. And what we really need to do is to evaluate the shear strength of your unsaturated rooted soil. So in this case, it's just a bare soil. We can utilize the extended mole Coulomb failure envelope, and then shear strength contributed by the cohesion, friction angle, and also some suction effect over there. So for the plant hydrological effect, it's considered the root-induced changes in the soil hydraulic properties as well. So we try to consider this in this term here. So the suction effect is associated with the water retention curve at this point, because this degree of saturation is related to water retention. And then we can input the water retention model from root to soil in this part. Okay, and that's how we consider the second hydrological effect in this simple equation. So in terms of mechanical reinforcement, we use a relatively simple model rather than the anisotropic behavior that we observed in the first part of my presentation. So in this case, the root cohesion has been used, and assume that the friction angle is doesn't change by root, which kind of makes sense in this kind of geometry, because we are concerning a slip surface that is parallel to the slope surface, and that is more or less following a direct shear stress path, or I would say closer to that stress path than the compressional extension. So in this case, the anisotropic behavior may be less significant. Of course, we are also assuming the root orientation is perpendicular to the subsurface, so that we can estimate the maximum reinforcement by the root using this simple Wool's equation, famous Wool's equation developed in the 1960s. So that equation is relating the root cohesion with root tensile strength, and also the amount of root biomass available across the slip surface. Okay, so this is how we captured it. And by the way, this K is an empirical factor to consider to factor down the potential overestimation of the root cohesion here, because we are using the root tensile strength, assuming all the roots were broken during the shearing, which perhaps is unlikely during shearing. And that's why this is a correction factor for this effect. So perhaps this is my last result slide, and this is the factor of safety plotting along depth, and you will see multiple lines here. I will go through with you. So bare slope here is without any reinforcement. You will see in the shallow part of the slope is unstable because the factor of safety less than 1, only up until in the deeper depth when the soil weight is sufficiently large to overcome the shearing. So if you only consider the mechanical reinforcement without any hydrological reinforcement, you will see this blue line behind it, okay? Sorry, this is red line, but it's superimposed at the back of the slide here. So you see in the top 0.5 meter, the slope is stable, but beyond that is unstable following the trend of the bare soil. So when hydrological effect was not considered. Now, from the modeling, we are able to break down the individual effect. So when I say H1, that is just associated with the transpiration effect by the plant, okay? So that is represented by the green dashed line, which again overlapped almost the previous mechanical only case here. So in other words, the transpiration effect has minimal effect on the factor of safety during this 1 hour intense rainfall. Okay, so if you look further on H2, which is the hydrological effect, only considering water retention curve, okay? Quite surprisingly, if you look at the blue dashed line here, again, it's overlapping the previous 2 cases. So that implies the water retention, although is being affected by the root, but it is not significant enough to change the factor of safety, okay? However, if you look at the H3, which represent the hydrological effect on the water permeability function, and that is represented by the purple line, you see a huge effect here, okay? So the whole slope is stable, even below the root zone, okay? So the water permeability function play a much more significant role than the water retention curve by the root, okay? So obviously, when you add up all these 1, 2, 3 hydrological effect together, become H, which represented by this solid red line, is almost overlap the M plus H3 cases. So this further highlights the significance of the water retention, the water permeability function effect by the roots. Okay, so just very quick conclusion remarks. Transpiration is not the only mechanism of transpiration effect, and perhaps not very significant in a short period of intense rainfall. But we shouldn't forget about the potential changes in soil hydraulic properties by roots in terms of water retention curve and the permeability function, okay? And the root growth and root decay could play a role on these 2 parameters as well. And we have derived a new void ratio function to capture this root effect, purely considering physical effect, okay? And relatively speaking, the permeability function changed by the root is more significant than the case for the water retention. And that is exactly what we have been focusing in our current research, and look at more details on how the conductivity function being affected by the roots more fundamentally. Okay, so that concludes my presentation, and I thank you very much for your attention, and I welcome any discussion in the Q&A section. Thank you. It's a very good question that has been asked even up to today in the literature. Now, in the literature of mechanical reinforcement, there have been many root reinforcement models, but broadly speaking, there are mainly two types. One is the root breakage model, one is a fiber bundle model. So the first type is what I've shown here in the slide, if you can see here, is from the very famous Wool's model in the old days. So they consider only breakage in the roots, assuming all the root has been fully mobilized during the shearing. So that may not be that realistic in application, because we rarely see all the roots being broken in shearing, because they could be quite ductile compared to the soil. So then there are another class of modeling, we call it the fiber bundle model, which takes into account also the root Young's modulus as well, so elastic modulus. So that perhaps could also capture the root reinforcement and also through the pull-out resistance as well. So this is something relatively new in the literature, although it makes sense to us, right? But it's still quite complex things to model in the nowadays literature. So if you ask me the accuracy of root tensile strength approach for calculating, the short answer is not very much. But there are some studies like applying this K empirical factor to tune down the root cohesion to not to overestimate it. But obviously it's empirical. So the physical reason of tuning down it is you need to consider the slippage mechanism or pull mechanism in that root reinforcement model. And now we have been working on my student, which is focusing on the first part of the research, mechanical reinforcement, developing some sort of failure criterion, hopefully more theoretically address this kind of problem in terms of accuracy. So in short, there's no quick accurate cohesion function for you to use to estimate slope stability. Oh, wow, that's another, you're asking a lot of my current research now. So yeah, that's very true. So now we are looking at, most of the existing research is looking at a snapshot on what happened at this time. So now we are trying to look at, 6 months, 12 months, 18 months, and 24 months. How would the root tensile strength changes first before the root reinforcement? And that's not an easy study to go for, because you have to have a very dedicated PhD student that is able to wait longer enough to collect the data, because root is a natural material that you cannot accelerate the decay process. So they have to stay in the field, in the lab long enough to get the data. However, we are quite fortunate to have this kind of researchers, with my collaborators in Thailand. And we do collect some interesting data. And for the vetiver grass, for example, we did quantify how the decay by burning and by the herbicide chemically decay the root. How would that affect the tensile strength? So those work is now under review by some journals. I hope I can come back sometime later in any presentation so that I can share the latest outcome. So I suppose you refer to the work in this slide. So it's just a small tube, typical small tube tensiometer you can collect in the market. And the RNG value of the ceramic disc is 100 kPa. So if you look at the results here, because we are dealing with a pretty sandy soil, the suction is not that high. So 100 kPa of RNG value would be more than sufficient in our case. So we are not using high capacity one in this case, which actually give us more problem because a lot of malfunction during the test. So that's a typical one. And I just drill many holes over there and put a lot of sensor to the middle of the soil. And that's how we get the suction directly, matrix suction. Or did you back calculate from the graph size? Yeah, so no, we didn't. We put both tensiometer and moisture probe in that big drums. We have quite a lot of space for this heavy instrumentation. This is something we are working towards on the biochemical effect. But we have to be careful on this, on elaborating the research, because understanding the roots in the soil is, the root tip will release the mucilage, affecting the soil around the roots. And that zone of effect is pretty narrow. We call it rhizosphere. it's talking about in micro-millimeter scale around that particular root. So we really wonder whether that affects, now for sure that the soil around the root must be affected biochemically by those mucilage. But whether that would affect in the engineering scale, in a soil scale, is sufficient enough, we are not sure. And we are doing some sort of a the pilot test to see the significance of the overall behavior. Now, definitely, agricultural people may argue this is extremely important around the soil-root interface. But overall speaking, we are not sure, and we are still testing it. Yeah. That requires the understanding from, the knowledge from the plant people. So we have been collaborating with a lot of great plant scientists. And vetiver actually, not just because of from the engineering perspective is impressive, but also the morphology, as I said, because it's deep-rooted. We have, before we elaborate all these experiments, we really have to be careful on the root morphology. Let me see. Okay, so this slide. Yeah. So we have to identify correct sort of ecological engineer from landscape perspective first. So once we agree on that species is appropriate for landscape, first of all, and then secondly, we have a sufficiently convincing root morphology, then we elaborate our investigation. Otherwise, if you select some shallow-rooted species, it's no use for slope stabilization purposes. So I suppose the answer is we need the input from the ecological people or the plant people to advise us, okay, this is a good species. From landscape, from root morphological perspective, then we investigate how that affects the soil behavior. Yeah. A suction function, I suppose you meant the water retention curve. Now, the water retention curve is by a modified Van Gunnarton equation. When I say the classic one is the Van Gunnarton in 1980, but then I used the Gallipoli modified version, which takes into account deformable soil in that Van Gunnarton model. And then I further elaborated by introducing the varieties of rooted soil into this model. So it's neither purely flatland type or a Van Gunnarton type. But if you are referring to the permeability function, I'm just using the Van Gunnarton, a pure Van Gunnarton, nothing modified. The only modification is on the saturated permeability using this empirical equation. Yeah. Now, I have been always challenged, that most of the Google pictures, if you look at it, on slope failure with vegetation. So why bother vegetation? Because you see the real case history, all failure with almost vegetation. So why do you want to investigate? So always my answer is, we haven't identified correct species for that particular case. So as I said earlier to your question, Chair Lady, so is working. We have to work carefully with the ecological people to select appropriate species so that the root according what we need. Okay, so we couldn't simply argue, say, okay, you see vegetation with failure or in the case history, then the vegetation is not very useful. So to answer your question, to reproduce the theory, no, just because those existing vegetation with no information, they are just, invasive species perhaps, or some naturally occurring vegetation with no information on the root morphology, then it's difficult to, do this forensic study, I call it, So no, the answer is no. Unfortunately, I can't. Okay, if you refer this particular calculation, it's basically MATLAB. We code everything by discretize it using finite element method, but it's a very simple method. It's 1D, so you can even use finite difference to solve this partial differential equation. That's the difficult bit in MATLAB. But then for this factor of safety calculation is very straightforward. You don't even need an Excel. You just use hand calculation. You can work on it. Once you know the suction at different depth, then you can plug into the equation using your calculator. Then you get the factor of safety immediately. The difficult bit is to solve that partial differential equation in MATLAB. Yeah.